Our next topic is prime and composite numbers. So first, some definitions. A prime number has exactly two distinct positive divisors. Now chances are there's a definition of prime number that you have memorized which says that a prime number can only be divided by itself and 1. And that's a pretty good general definition, except for one thing. If you think about what the smallest prime number is, you might think that the smallest prime number is 1. But it isn't. The smallest prime number is actually 2. 2 can only be divided by itself and 1, that's true. And 2 has exactly two distinct, meaning different, positive divisors. That would be 1 and 2. The reason why 1 is not considered a prime number is that 1 only has one distinct positive divisor, and that would be the number 1. So what are the rest of the prime numbers? Well, they go on infinitely, but if we look at the ones after 2, 3 is prime, 5 is. Now 4 isn't because 4 can be divided by 1, 2, and 4, so it has 3 distinct positive divisors. 7 is prime, 6 is not, because 6 has 1, 2, 3, and 6 as divisors. 11 is prime, 13's prime, 17's prime, 19 is prime, 23 is prime, 29 is prime, and the primes go on forever and ever and ever. Now, if a number is not prime, it's called composite. A composite number has factors other than itself and 1. So we already said that 6 was not prime because 6 had more than 2 distinct positive divisors. 6 has 4 positive divisors, and that makes it a composite number. One way to organize the information that we're going to need to gather about these numbers is to make what's called a factor tree. And we can use a factor tree to find the prime factors of a composite number. So let's use 24 as an example of how to build a factor tree from a composite number. The first thing we want to do is think about what two numbers can multiply together to give us 24. And obviously there's more than one answer to that question. We could say 2 times 12, we could say 3 times 8, we could say 4 times 6. We don't want to think of 1 times 24 because we're looking for factors other than 24 that are factors of 24. So pick a path. I'm going to start with 6 times 4, but you could start with any two numbers that multiply to give you 24. Now we look at each of those factors and try to decide if we can write those factors as a product of two other numbers. Well, 6 certainly can be rewritten as 2 times 3, and you'll notice that 2 and 3 are both prime. Anytime we find a prime number in the factor tree, we're going to circle it because we have nothing else to do to continue the tree once we found a prime factor. On the other hand, that 4 that we had when we said that 24 is 6 times 4, 4 is not prime. So we can continue to factor 4 into 2 times 2. And since both of those are prime, we'll circle them. Now you can see that we have found all of the prime factors of 24, which means we can rewrite it as a product of prime factors. Now, just to show you that it really doesn't matter how you get started on this process of finding prime factors of a composite number, what if we had decided to start 24 off by thinking of it as 8 times 3? 3 is prime, but 8 is not. 8 can be rewritten as 2 times 4. 2 is prime, but 4 is not. 4 is 2 times 2, and both of those 2's are prime. If you look at the circled numbers in each of these trees, you'll see that the circled numbers are identical. We have 3 factors of 2 and 1 factor of 3. So it doesn't matter how we get started with factoring a number to find its prime factors, as long as we start with two numbers that will multiply to give us that number. We can write the prime factorization of 24 by gathering up all those circled numbers, all those prime factors, and showing that if we multiply them together, that we will have the number 24. And because the 2's do repeat as factors, if we wanted to, we could write that as 2 to the third times 3, because there are 3 factors of 2. Now we said it doesn't matter how you get started with this factor tree, as long as you find two numbers that will multiply together to give you the number that you're trying to rewrite, you will in the end have the same factors. And that's such an important concept that it has its own name. It's called the fundamental theorem of arithmetic, which is that every composite number can be written as a product of primes in one way only. So the bottom line is, when you're trying to find the prime factorization of a number and you're building a factor tree in order to find that prime factorization, it doesn't make a bit of difference how you get started, because in the end there's only one way to factor that number. Now we talked about some prime numbers, and we went up through 29 in listing some primes, but the primes go on forever and ever. So what if we have a number bigger than that, like 43, and we want to know if 43 is prime or is it composite? Well, one thing we can do is to look for prime factors of 43, because if 43 is composite, it has prime factors other than itself in 1. So let's take that 43 and start to divide it by some prime numbers to see if we can find any prime numbers that are divisors of 43. Well, the smallest prime number is 2. So if we try to divide 43 by 2, now here's where your divisibility rules might help you. 43 is odd, so we know we can't divide it by 2 without a remainder. In fact, it would be 21 remainder 1. So 2 is not a divisor. It's not a factor of 43. The next prime number after 2 is 3. So is 3 a factor, a divisor of 43? Well, it isn't. If we try to divide 43 by 3, we get 14 with a remainder of 1. Well, 5 is the next prime number, so it's the next possible prime factor of 43, and 43 cannot be divided by 5 without a remainder. The next prime number after 43 is 7, and if we try to divide 43 by 7, once again we get a remainder. The next prime number after 7 is 11. If we try to divide 43 by 11, we once again get a remainder. So what you see we're doing is we're trying to take this number and find out if it has prime factors other than itself in 1. If it does, it's composite, and we haven't found any prime factors in 43 yet. So we're going to conclude that 43 is prime. Now what you may be wondering is, okay, we were dividing by all these prime factors. When do we know how to stop? What's the point where we say, okay, we've looked long enough, we haven't found any prime factors, so this number must be prime? Well, there's actually a way to tell how far you have to go in testing to see whether prime numbers are factors of another number. So let's look at that. Let's see what was the largest possible prime factor of 43. Now we have already established that it doesn't look like there are any prime factors of 43, but what was the biggest one that we really needed to try? We went all the way up to 11. Did we need to go that far? So here's how we figure this out. We know that we're looking for prime factors of this number. So let's think about these prime numbers. 2 is the smallest prime number, and let's also think about the squares of the prime numbers. So 2 squared is 4. 3 is the next prime number, and 3 squared is 9. 5 is the next prime number, and 5 squared is 25. The next prime number after 5 is 7. 7 squared is 49. 11 is the next prime number after 7. 11 squared is 121. Obviously, we could keep this list up and keep listing prime numbers and their squares. But what we're looking for in this list of numbers is we're really going to concentrate right now on this list of squares. And we're going to try to figure out where our number 43 would fit in that list of squares. Now, if 43 is in that list of squares, then it's definitely not prime, because it is the product of two prime numbers other than 1 itself then. But 43 isn't in the list of squares, and it would fit right there. It would fit between 25 and 49. So what does that tell us? Well, first of all, it tells us that 43 is not a perfect square. At least it's not a perfect square of a prime number. But the other thing it tells us is exactly how far we have to look to find prime factors of 43. The largest number we would have to look for to see if it's a prime factor of 43 turns out to be 5. And the reason we need to look at 5 is that 43 is bigger than 25. That would be the largest square of a prime number. So the smallest number, or excuse me, the largest number we need to look for to see if it is a prime factor of 43 is that number 5. Now this is the work we did to try to figure out if 43 was prime. We actually did a little more work than we needed to. We only needed to do those first 3 tests. We only needed to see if we could divide it by 2 and by 3 and by 5. So let's take this idea and see if we can use it to test to see if 113 is prime or composite. And before we actually try to divide it by prime numbers, let's think about this list that we had of prime numbers and their squares and see where the number 113 would fit in that list. And remember, where we're trying to fit it in is in the list of squares of the prime numbers. 113 would fit in right there between 49 and 121, which means the largest prime number that we're going to have to test to see if it is a factor of 113 is the number 7. So we only have 4 numbers to check to see if they will divide into 113. So we'll start with the 2. 2 is definitely not a divisor of 113 because 113 is an odd number. We can check the 3. Now we have a test for 3. Divisibility test for 3 is add the digits. So 1 plus 1 plus 3 is 5. No, you can't divide 5 by 3, so that would be a no. Is 5 a divisor of 113? Absolutely not. It does not end in 0 or 5. And then does 7 divide into 113? Let's see if I mentally do my cross out double subtract rule. Cross out 3, double it, I get 6. 11 minus 6 is 5. Nope, can't divide that by 7, so that would be no. So we've tested every prime number that we need to test to see if we have any other prime factors of 113. So the bottom line is 113 is a prime number. So let's talk about some divisors of composite numbers. Divisors are numbers that divide into another number without a remainder. Now we've just looked at prime numbers, and prime numbers can be divisors of numbers, but we can also have composite numbers that are divisors of numbers. So if we're going to list all the numbers that are divisors of 12, we want to list every number that will divide into 12 without a remainder. 1 is a divisor of every number. 2 is also a divisor of 12, as is 3, and 4, and 6, and 12 is a divisor of 12. So we have 6 numbers that are all divisors of the number 12. What if we are asked how many divisors does 1,500 have? Now this is a little trickier question. If we're going to answer the question, how many divisors, I suppose we could do it by trying to list all of them. So we could say, well, 1 divides into 1500, 2 does, 3 does, 4 does, and we could continue that on. We'd have a lot of numbers we'd be listing, and we might miss one. But you'll notice it didn't ask to list them. It asked how many divisors does 1500 have. So there's a way to tell how many divisors a number will have. And it involves taking this number and making a factor tree to find the prime factorization of it. So let's do that. 1500 I know is 15 times 100. 15 is 3 times 5. And 100 is obviously 10 times 10. Remember, we're going to circle all the primes when we find them. Each of those 10s is 2 times 5, and both of those are prime. So in the end, we have a factor tree that shows the prime factorization of 1500 to be 2 squared, because we have 2 factors of 2, times 3 to the first, because we have 1 factor of 3, times 5 to the third, because we have 3 factors of 5. Now, it may seem a little strange to have written this with exponential notation, and it might seem strange to have written 3 as 3 to the first, but there's a reason why we need to look at those exponents. If we have the prime factorization of this number written in exponential form, the exponents are going to answer the question for us about how many divisors does 1500 have. Because what we need to do to answer that question is take each of those exponents, the 2 and the 1 and the 3, add 1 to each of them, so that's 2 plus 1, and 1 plus 1, and 3 plus 1, and then multiply those numbers together. And that result, 24, is the answer to the question, how many divisors does 1500 have? It's not telling us what the 24 numbers are. It's just saying that if we listed all the divisors of 1500, we would find 24 numbers. So our next topic is greatest common divisor and least common multiple. We've just looked at numbers that are prime numbers and numbers that are composite numbers, and we've talked about what divisors are. Divisors will divide into another number, and all of those ideas are related to these two ideas, greatest common divisor and least common multiple. So first of all, definition. The greatest common divisor, which we can abbreviate GCD, of 2 or more integers is the largest integer that divides the numbers. So we're looking for a number that will divide into 2 other numbers without a remainder, and we're looking for the largest of those numbers. So we have several methods for finding greatest common divisor. Let's use the example of greatest common divisor of 8 and 20. They're nice small numbers to work with. It's going to be easy to see what's going on when we use these methods. And the first method we're going to look at is called the intersection of sets method. So the first thing we want to do is find all of the divisors, all the factors of both numbers separately. So factors of 8 would be 1, because 8 can be divided by 1 without a remainder, and 2, because 8 can be divided by 2 without a remainder, and 4 and 8. So we have 4 numbers that are factors of 8. And the factors of 20, the numbers that divide into 20 without a remainder, are 1, 2, 4, 5, 10, and 20. All right, so we've got the factors, we've got the divisors. We're looking for the greatest common divisor. So we've got the divisors. Now let's kind of work backwards with the words that are in the name of this greatest common divisor. We found the divisor. Let's move backwards and look for what these lists have in common. So the common factors, the factors we see in both lists, would be the 1, the 2, and the 4. So those 3 numbers will all divide into both 8 and 20. But we don't just want the common divisors, we want the greatest common divisor. So the greatest common divisor is the biggest number in that list, which is the number 4. So the greatest common divisor of 8 and 20 is 4 because 4 is the largest number that divides into both 8 and 20 without a remainder. Here's a second method we could use to find the greatest common divisor of two numbers. It's called the prime factorization method. For this method, we need the prime factorization of both numbers, which we've already seen we can find if we make a factor tree. So if we take 8 and we factor it into prime factors, we can see that 8 is equal to 2 times 2 times 2. And if we do the same thing for 20, we'll see that 20 is the same thing as 2 times 2 times 5. So we'll write each of these numbers as a product of prime numbers. And now what we're going to look for is the factors, the prime factors that these two numbers have in common. Well, they have a pair of 2's in common, and they have a second pair of 2's in common. So these are the factors, a 2 and a 2, that the two numbers have in common. And in order to find the greatest common divisor, the greatest common factor, what we have to do is find the greatest number we can get by multiplying these factors back together. So 2 times 2 is 4. We're getting exactly the same thing that we did with the intersection of sets method. Now what if we have larger numbers? We want the greatest common divisor of 42 and 63. Well, either method will work, but you may find that as the numbers get larger, that the intersection of sets method can sometimes get a little bit awkward. Because in order to use this method, we need to be able to list all the factors of our numbers. And sometimes it helps when we're listing them to pair them up. So for example, if I'm looking for the factors of 42, if 1 is a factor, 42 is also, because 1 times 42 is 42. If 2 is a factor, then 21 is also, because 2 times 21 is 42. I know that 3 is a factor of 42, but that means 14 is also, because 3 times 14 is 42. So sometimes that method can help you find all of those factors and make sure you don't miss any of them. Factors of 63, we can do the same thing. 1 is a factor, so 63 has to be, because 1 times 63 is 63. 3 is a factor, which means 21 is. 3 times 21 is 63. And 7 and 9 are the last two factors. So for the intersection of sets method, the larger the numbers get, the more difficult it gets to make sure that we haven't missed a factor. But it is possible to go about this kind of methodically and to pair up your factors so that you don't miss any of them. All right, so that's our factors, that's our divisors. Now we want to know what these two sets have in common. So the numbers that we see in both lists are 1 and 3 and 7 and 21. Now, although those are all common factors, we want the greatest one. So the greatest common factor, the largest number in that list, is 21. 21 is the largest number that divides into both 42 and 63 without a remainder. Let's try the same two numbers with the prime factorization method. Remember, we need to break down these two numbers into a product of prime factors. Factor trees can help you do that. So 42 is 2 times 3 times 7, and 63 is 3 times 3 times 7. So we're looking for factors that are shared between the two numbers. There's a pair of 3's that are shared and a pair of 7's. And because these are factors, we can multiply factors together to get the largest factor that the two numbers have in common. So 3 times 7, the product of those two common factors is 21. Now there's one other method that we can use to find the greatest common divisor of two numbers. It's called the Euclidean Algorithm. And it's really useful when you're trying to find the greatest common divisor of really large numbers. So the Euclidean algorithm says that if you're trying to find the greatest common divisor of two numbers, which in this case are a and b, then that's the same thing as the greatest common divisor of r and b, where r is the remainder when a is divided by b. Now that makes this sound pretty mysterious, so let's go through this process of using divisions and remainders to find the greatest common divisor, and let's go ahead and use 42 and 63 because we know that the greatest common divisor is 21. We've already done that in two other ways. So here's how we get started. We're going to do a division with 42 and 63. We're going to divide the larger number by the smaller number. So 42 goes into 63 once, with a remainder of 21. Now what's important at this point is to pay attention to the remainder. If the remainder is not 0, we have not found a divisor. Remember, in order for a number to be a divisor of another number, we have to have a remainder of 0. We don't have that yet. But since we don't have a remainder of 0, we're going to continue this process by taking the number that we have for the remainder and the divisor that we used, and we're going to repeat the process of division using those two numbers. So 42 divided by 21. Well, 21 goes into 42 two times with a 0 remainder. So we know that when we have a 0 remainder, that the number we divided by, the divisor, is a factor of the number. So we know that 21 is a factor of 42, and 21 was also a factor of 21. So the last remainder that, or excuse me, the last divisor that you get once you have a remainder of 0 is your greatest common divisor. So in this case, the greatest common divisor is that 21. Let's try this same method one more time with some even bigger numbers. So let's say we want to find the greatest common divisor of 1,824 and 7,448. So we're going to divide, and we're going to pay attention to the remainder, which in this case is 152. If the remainder is not 0, we have not found the greatest common divisor. If that remainder were 0 at this point, then the 1,824 would be the greatest common divisor. But it's not, because the remainder isn't 0. So we're going to take the 152 and the 1,824, and we're going to do a division again. Now we're going to pay attention to what that remainder is. If the remainder is 0, which it is, then we're done. If the remainder is 0, then the last divisor we had, which in this case was the 152, that is your greatest common divisor. Now what would we have done if the remainder had not been 0? It would not have been a problem. We would have continued the process. We would have taken the remainder, which wasn't a 0, and we would have taken the last divisor, which was 152, and we would have continued the division process. And you do that until you have a remainder of 0. Once you have a remainder of 0, the last number you divided by is your greatest common divisor. Now there is a way to check this. How can we tell that 152 is the greatest common divisor of these two numbers? Well, if it is, then we can rewrite each number as 152 times some number. And yes, we can. 1,824 divided by 152 is 12, so 12 times 152 is 1,824, and 7,448 divided by 152 is 49, so 49 times 152 is 7,448. The least common multiple of two or more numbers is the smallest number that is a multiple of all the numbers. Now remember what multiples are. Multiples are numbers that we get when we take a number and multiply it times the counting numbers, times 1, times 2, times 3, times 4. So we're looking for a smallest of those multiples that two numbers have in common. Let's find the least common multiple of 8 and 20. We've got two methods we're going to look at to do that, and they have exactly the same names as two of the methods we used for finding divisors. The intersection of sets method finds a set of numbers that makes up the multiples of 8, which would be 8 and 16 and 24 and 32 and 40, and they continue on and on and on. And a set of numbers that make up the multiples of 20, which would be 20, 40, 60, 80, and they go on and on and on. Now obviously these are infinite sets, but we're still looking for the intersection of those two sets. We're looking for what do they have in common, because those would be what we would call the common multiples. So the multiples that are in both sets are the 40 and the 80, and 120 would be in there, and that set would continue on. It's infinite. But of those numbers that are common multiples, we want the smallest. We want the least. So the least common multiple is the smallest number in that set of common multiples, which is just 40. There's also a prime factorization method for finding least common multiple, and like the prime factorization method for greatest common divisor, this also requires us to find the prime factorization of the numbers we're trying to find the least common multiple of, and we'll see that a factor tree works very nicely for that. So if we make factor trees for 8 and 20, we can see that 8 is 2 times 2 times 2, and 20 is 2 times 2 times 5. So to use this to find the least common multiple, the first thing we'll do is find what multiples, what factors they have in common, which would be a 2 and a 2. Now you may recall that that actually would give us the greatest common divisor of 8 and 20. But we want the least common multiple, so we need to have a way to express a common multiple of these two numbers that has all of the factors of both numbers. They share a 2, they share another 2, but then there's a 2 that they don't share and a 5 that they don't share. And if we multiply those numbers together, we have the least common multiple of 8 and 20, which is 40. So if we were to list the multiples of 8 and 20, 40 is the first that we would find that they have in common. So let's look at one more way to think about least common multiple and greatest common factor, greatest common divisor. And we're going to use these two numbers, 12 and 18, as an example. We could actually use a Venn diagram to see how all these factors of these numbers fit together to give us greatest common factor and least common multiple. So keep in mind what a Venn diagram looks like. It has attributes. In this case, we're looking for the factors of 12 and the factors of 18. 12 is 2 times 2 times 3, and 18 is 2 times 3 times 3, if we think of them as a product of their prime factors. Now look to see what factors they have in common. Whatever factors they have in common will go in the intersection of the two sets in our Venn diagram. So this 2 that they have in common would have to go inside the intersection. And the 3 they have in common would also go inside the intersection. But there's other factors that they don't have in common. The 12 has a factor of 2 that the 18 doesn't. So it will go in this part of the Venn diagram. And the 3, that's the factor of 18, that is not shared with the 12, will go in that part of the Venn diagram. Now the intersection of those two sets is where you find the greatest common factor, the greatest common divisor. And if you look at all of the factors that are included in the sets, which would be a 2 and a 3 and a 2 and a 3, and you multiply those together, you have the least common multiple of the two numbers. So we're really doing exactly the same thing that we did with our other methods for finding least common multiple and greatest common factor, but we're just representing it a little bit differently. We're representing it as a Venn diagram. So that's the end of our discussion of least common multiple, greatest common factor, or greatest common divisor. We're going to be using these ideas when we start to work with fractions very soon.